Well, let's start. So I got to notice that Joe's out of the class, so we're down to five. So and of the five, uh, I think we know Spencer sometimes has issues. William's going to be deployed for just a week, so he should be okay. So hopefully everyone else is doing okay and not panicking. Okay. I wanted to do a little bit more discussion about verification validation because there were a couple of definitions that I didn't explain fully, so I wanted to go through them. These two papers that are on the Canvas site by Balchi, I think are really good. They're readable. They're not full of so much extra math that you have to take a course in lambda calculus to understand what's happening. Um, and they present, I think, really essential information. Um, they're also, if you read them both, you'll see that the author is using kind of a cheap trick that sometimes professors do to get their publication count up. It's effectively the same paper twice, effectively. And so this is a narrowed version of the paper we walked through yesterday. And in that paper we walked through yesterday, there was a table that said, here's some characteristics of verification, validation, accreditation. And basically this paper is just that table expanded. And he kind of reorganizes some of the table rows, but basically the same thing. So the thing I wanted to walk through, um, just walking through the principles, and you can see we talked about this yesterday, right? Because it was in the table. This VV and oh, what's he calling T? I'm sorry. He replaced the T with a testing, verification, validation testing. Must be conducted throughout the entire life cycle. We talked about that yesterday. There are mechanisms by which you can build a model of your system, and then you use that model throughout the entire life cycle to convince yourself that you're on the right track. That is extra work to build that model. And again, there are people particularly in the formal and software verification field and the model-based quality assurance software people who are pushing for that in industry. And then there are always the issues of you have to sell it to management, right? Because what management sees is an additional cost. This is, by the way, something that you don't get to experience that much in academia. In the business environment, there are going to be people always asking you to justify the cost of what you're doing. And so it's difficult in some cases because if there's, let's say you do something good and you prevent a bad thing from happening. What was the cost of that bad thing not happening? If you say, oh, the bad thing happened, it would have cost us $1 million, but it didn't happen. So I don't know how to tell you that the $100,000 I spent actually saved you $1 million later on because the $1 million never showed up. All they see is you cost them $100,000. So it's difficult to get that kind of cost benefit in play. Now, once the bad thing happens, everybody is your friend, and they'll be happy if you say, you know what, in the future we can prevent this by doing process X. Then they're like, we better do process X. But typically, people have to experience the downside before they'll invoke the rule. Okay, we talked about this. The outcome shouldn't be considered as a binary value where the model is absolutely correct or incorrect. There's a range of correctness. We're all engineers in here. We all understand. No, wait, you're computer science, right? Well, close enough. So you need correctness. In the engineering world, we talk about engineering accuracy. So if we get within 10%, we're happy as ducks as engineers. So what's happening here, since almost always the results of the simulation are statistics based, then we're going to say we have some degree of confidence in the system. It's not like it's correct or incorrect. And of course, as we discussed later on, it's only correct with the things that we were building it for. So that's number 3. It's only built with respect to study the objectives, and its credibility is judged with respect to those objectives. As we discussed yesterday, even with respect to those objectives, people may not believe what you have to tell them. And if you're telling them bad news, they really don't want to believe it. Right? There's an emotional response that will prevent them from believing it. And somebody who might have been Voltaire, might have been Mark Twain, might have been somebody else, said something along the lines of, it's very difficult to convince somebody of something when their income relies on believing the opposite. So, just because you have a great system and you believe the results doesn't mean that other people will. And of course, you can't try to use your model for things it wasn't designed for. That leads into this one, which is requires independence. So if you're developing the system, you will incorporate bias. That's just how people are built. So we want to have an independent group of people if possible. What that really means is if you're in a really small company where everybody wears many hats, you can't achieve that independence. There's not enough people. In a large company, you may have a development group and a testing group, and they're separate people. And so you get some degree of independence. It's difficult and requires creativity. That's accurate of all kinds of testing for software. But there are mechanisms that we can use. There are best practices that we can use. The model can only be claimed for the conditions for which the model is tested. So this one's slightly different from what showed up on the table yesterday. So if you say, oh, I've done a bunch of validation tests. So here's all of my scenarios that I used as inputs, and here's all the outputs, and I believe that this is a valid model. It technically is only valid for the scenarios that you tested it for. If you try to add a new scenario, you may or may not be getting good results. And it's difficult to claim good results. You can only claim it if you can try to make some analytical leap as to why this new scenario is not so different from the tested ones that it's still valid. And obviously, the further away you get from the scenarios that you initially intended, the tougher it is to make that claim. And people will abuse the system. If there is already an existing model, they may throw in a whole brand new scenario for which your model, quite frankly, falls apart. And then they don't know that, and they'll use the results and get bad results. Complete simulation model is not testing. That's always true for any kind of software. Simulation must be planned and documented. That's the one that is the most abused because, again, often we're doing research in the way that you're doing it now. You're doing it for a class project, or you may be doing it for a paid research grant for an academia, or you may be just trying to get your master's degree or your PhD, so you're doing some kind of research. And generally, the documentation is the last thing you worry about, right? You're just trying to hit all the deadlines to get this thing delivered in time to get it to the customer or hit the date that the university provides for your last day of defense. Here we go. This is the stuff that I did not explain that well yesterday. This is actually not quite what was on the table. Type 1, 2, and 3 errors must be prevented. And so they define right here what these are. Type 1 error is committed when the simulation results are rejected, when in fact they are sufficiently credible. So that's what I was talking about earlier. You may find that you have a valid model, you have credible results, and you may reject them for whatever reason, but more likely somebody else will reject them. You have your simulation results, you're going to report them out to people, and they may not accept your results. You can also imagine there may be a situation where there are two different simulation models and they're giving different answers. And now the person that is assessing things gets to choose which model they think is credible. The most common example of that, which we're coming into now because we're in hurricane season, are the spaghetti models. And the European model versus the US model, they tend to have divergence into where they think a hurricane track is going to go. So you've seen this, right? The other form of that rejection, as I said before, if somebody hires you to build a simulation, run a simulation, and do some kind of analysis, and the results you give them are not what they wanted to hear, there is a strong possibility they will reject those claims. Oh, and by the way, while you're building the model, they're going to be telling you loud and clear what they want to hear. And what a great opportunity for you to inject bias into your model, right? So you're going to make sure that your model tells them what they want to hear. That happens a fair amount too. Type 2 errors are invalid. Simulation results are accepted as if they were valid. So type 1 says the results are valid, but we reject them. Type 2 says the results are not valid, but we accept them. Why would that be? Well, sometimes it's out of ignorance. People are not understanding when they use the simulation what the boundaries were in terms of the kinds of conditions for which this thing is valid. It also could be, again, we're not rational. It could be, oh, I'm going to accept this because it told me what I want to hear. And then type 3 is just we solved the wrong problem. In other words, in terms of software engineering, we didn't build the right thing, right? We failed the validation test from a software engineering standpoint. So, but what's happening there is we solved the wrong problem. Uh, you would think that that's something that, of course, we would never make that error, right? But life and natural systems can be very subtle sometimes. So really what might happen, let's say that there's some phenomena that you want to investigate. I want to understand why this phenomena occurs. I don't know. The trees are dying. I want to understand why the trees are dying. Okay, so I'm going to model the system. And it turns out the trees are dying because of some fungus. But you assumed, you didn't even have any thought that there was a fungus going on. So you put in atmospheric conditions and you tested for atmospheric conditions. Well, you're solving the wrong problem technically, right? Because you're asking, you think you're asking the right problem, why are the trees dying? But you're actually solving the wrong problem because you're going with, say, an climatic effect as opposed to some biological effect. So your model, quite frankly, is just off base. So there can be times when you think you're solving the right problem, and then it turns out, oh, wait, the actual cause and effect lies somewhere else. So, and since it wasn't included in our model, we've not captured it. Errors should be detected as early as possible. Yes, that's a cost savings thing. The longer you wait to discover a defect in your either in your model or in your software, the more costly it is to fix. And this is the other one, Principle 11. Multiple response problem must be recognized and resolved properly. And I thought I had it right yesterday, but I just wanted to confirm that what we're saying here is if you have multiple variables, we talked about this in experiment design a little bit. If you have multiple variables and you're doing a classic experiment where you're changing one at a time, what you're missing are the interactions between the variables. So what's happening here is if you have two or more output variables cannot be tested by comparing the corresponding model system input variables one at a time. They're using a univariate statistical procedure. In other words, they're saying in the classical form where you just change one variable at a time, yeah, you can find effects. But what you're not going to find are the interaction effects between variables. So what does that mean to be resolved properly? Notice there's no resolution. Is there no resolution? Oh, a multivariate statistical procedure must be used. That's the solution. What does that mean? It means, if you go back to your experiment design discussion, it means that you can do like a Latin square or Latin hypercube or some kind of a situation where you are changing multiple variables at the same time. And then you can do some kind of statistical technique, which was there was a paper that we had addressed there, some kind of statistical technique where you try to tease out where the interactions occur. And so you can do it. The initial way to do it is to try to do you tease out the individual variables, and there was a technique for that. But then the other form was, I think it was you did like a variable one, variable two plus, variable one, variable two minus, and you compared those two cases against each other to see if there was an interaction between variable one and variable two. There was also something, and I don't have any. I don't have work for it, but I published a paper a long time ago, and it's in your notes under the experiment design section. It's something called Pareto analysis after someone named Pareto, and basically it's another mechanism by which you can try to say, here's all the interaction, here's all the variables that we're changing, multiple variables at a time, and still trying to tease out the effect of one of them. And that effect of one of them will basically incorporate the effects of the interactions too. Yeah.
So then this is just for, say in my case, right? I change delay and the behavior of a node. But if it was both at the same time, that would be for this.
Yeah.
But if I went through and changed just one,
Yeah.
nothing. Changed just the other,
right.
Nothing.
Right.
And then changed
third thing.
Yeah.
Path length.
Yeah.
Yeah. So I think with yours, and again, what if you can justify that you do not believe there is an interaction, you can always do the one variable at a time classic form. In this case that you're describing, I don't see an obvious reason why there would be interaction. Now, there may be the way to find out would be to test, but I suspect that you can do you have completely different cases. The time delay with the same node behavior, but changing the time delay is valid because you're asking how about time to converge. Path length isn't independent from time delay. And then the idea of having the user modify the node behaviors is so open-ended. I don't think you can just call it a variable. You know, it's just a practice of have we achieved the ability or not? Because the actual result is based on what the user ultimately wants to program those behaviors to be. And I think, like we discussed the other day, the way you do that is you give them a menu of options.
Yeah.
We talked about testing the submodels does not imply the overall model is good. And again, that's because of emergent effects of when you combine the submodules, each one is effectively an agent. The agents are going to interact. You get emergent behavior. The emergent behavior is difficult to describe, hard to provide the boundaries for. Double validation problem. This is what was in the list yesterday, and I didn't describe the terminology accurately or effectively. The double validation problem is that you're saying that you are trying to validate your model by putting some inputs in and getting a result, and then you're going to compare it to the real world. But the real world has inputs too, or at least what you're considering is your initial scenario attribute values. So if you set up imagine you just set up a scenario by setting up, here's a bunch of, here's my geometry, here's my number of agents, here's the initial starting qualities or attributes of all the agents, go. And so from there, the system runs and it produces output. And you're going to use that for a validation test. Well, that means that you're going to go to the real world and you're going to look at, in the real world, the number of agents and the initial attribute values and all that good stuff, and the geometry or the configuration of the environment, all those things in the real world. And then you're going to map them to your inputs for your scenario. But the question is, did you even do that correctly? So you have to actually technically validate your input. Validate your initial conditions. By that, it means convince people that your input and your initial conditions actually match the real world scenario input or initial conditions that you're trying to duplicate. And this author is calling that the double validation problem because not only are you validating your model, you're validating that the inputs that you used for the validation testing were themselves valid. Notice the levels of detail. There's often these kind of meta levels, right? So if you said, oh, I modeled traffic and everything was great, and someone would say, yeah, but you only used 2 cars, and that doesn't match the real world, right? I can go to Clyde Morris and I can see there's way more than 2 cars. Well, your input was not valid.
Also, if you were standing there, like you said, clicking each card, but then like if you're also trying to track near misses and you're missing the near misses or something.
Right, exactly. So yeah, yeah. Right. So that's that problem. That's that problem explained. And then validity does not guarantee credibility or acceptance. We talked about that. Okay, and then he goes into techniques. Okay, so I just wanted to walk through that paper to provide some of the places in the lecture yesterday where I don't think I really fully explained what was happening. So give you a better explanation for those things. Now, having said all of that, in this class, the verification and validation portion of your project is minimal, right? Because we don't have time for it. We only have 6 weeks. So how are you going to do verification and validation? Yeah, see? Here's what you're going to do. And the trick is to document it so it's in your report. As you're building this thing out, like Williams already made a simple traffic model. Right? He can use that as verification to convince himself the model was built correctly. Right? So that's what you're going to do. It's normal while you're developing software to pause, compile, run, make sure it's working so far. Right? Those kinds of software development steps are really going to be a substitute for a proper verification and validation that you would do if we had, if we'd gotten a nice big fat grant from NSF and funded you guys for a year, you could have done proper verification and validation. But for a course situation with 6 weeks, we have to pick and choose what's going to be the most critical thing. So you already have a test design, right? Your experimental design. And you can throw in a couple of use those exact scenarios as validation. Now, again, with fuzzy cognitive maps, what does validation mean? It means you have a math model and you start out with a simple math model and convince yourself you got the same results, right? Start with a 2 nodes and 1 edge, or 2 nodes and 2 edges where they make a loop, and run a simple by hand where you know how many steps it takes to converge, run it in the model and see if it took the same number of steps to converge. That would be a verification of the model, right? It's also a validation of the model because you built the model correctly. You're matching the quote real world model. You don't have a real world to go to. The validation that comes with the fuzzy cognitive map world, if somebody chooses to use your fuzzy cognitive map tool to model, I don't know, takeoff delays at the airport, right? Now they can go to the real world and get takeoff delays at the airport and do validation of their model, but they're going to build their model using your fuzzy cognitive map tool. Since you're developing just the tool and you don't have a real world scenario that you are interested in, then you're not going to validate to the real world. The best you can do is verify that you built your model correctly inside the tool, inside the software tool. Now, if you also want to do some kind of, as a test bed, we're going to run a simple scenario that has a known result. There are people who have used fuzzy cognitive maps and they publish the results, and you could pull one of those in and call that a validation step because then you're showing that your model matches what those people got. Fair enough. Same thing with you. Rather than going out and counting cars, other people have published traffic studies to death. Find one that's as simple a model that you can build, right? Okay. So that was verification validation. The next couple of lectures have to deal with distributed and parallel simulation. And I think it brings in some really interesting topics. Almost all significant modeling and simulation products today are going to be either parallel or distributed in nature. Almost all of the commercial products are going to be that way. Now, if you're talking about something like MATLAB has a strong simulation component. What's it called? Simulink, something. That is not going to be parallel and distributed. And the reason is that's a tool, and it's a tool pretty much with the intention of it's going to be used by one person. And so there's no need to have the distributed and distributed in parallel. However, if you're building a product like a training product that's going to be used by the military, that's inherently distributed. So I mentioned earlier in the semester, if you go to, I think it's Tulsa, Oklahoma, there's these massive buildings with big boxes inside, and you can go inside the box. And when you do go inside the box, it looks like you're in an Abrams tank, or it looks like you're in a Bradley fighting vehicle, or, the inside of that is laid out as if you were in the vehicle. And then whenever you look out, what you're seeing is a monitor providing you with a virtual scenery. Well, each one of those has computers inside the unit. And each of those computers feeds to computers that are stitching all of the different elements together. So if I'm in one tank and you're in another tank, we get to see each other, just like in a video game. If I'm a character in a video game, you're a character in a video game, we get to see each other. We're participating in the same virtual space. So those are inherently parallel and distributed. And the reason that they are is because there's so many actors, one computer can't handle it. So almost anytime you're going to do training in a real-time system, you're going to run up against the limits of the real-time requirement pretty quickly, it turns out. Even with today's super fast computers. So what do? How do you get a faster computer? You get 5 of them. Right. So now you're either parallel or distributed. We'll talk about the difference in a second. If you are doing models like the spaghetti models for hurricanes, I don't know enough about them to know if the individual models are on a single machine or a parallel distributed machine. I suspect they're sophisticated enough. There's so much data handling. They want to get some results fairly quickly. I suspect that they're parallel, like in a cloud service. That's my suspicion. That would make sense to me, only because those models have become so sophisticated and they do many, 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 many computations. So once you get into this, what we call high performance computing with many, 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 many computations, it's really easy to get out of having one processor or one computer and jumping into a multi-processor system. Now, I have to be careful with that. Back when we started defining the terms of parallel and distributed, what each computer, each laptop, each desktop had one processor. Now they have 8, 16, right? So you still treat that logically as one processing unit, even though there's multiple processors internal to that one box. And then when you hook them up, that's when you start talking about whether or not they're parallel or distributed. They are intrinsically parallel inside. Now, you have heard the term, hopefully, you've heard the term parallel processing. True? You've heard the term distributed processing, maybe, probably. They are different. We use them as if they are the same almost all the time, but they are different. And here's the difference. In a technically parallel system, all of the processors have access to the same physical memory. So you have, like inside your machine now, your machine, let's say it has 8 processors in it. We think of that as one logical computer, right? One logical processor. But technically, if there's 8 processors inside of your laptop, that is a parallel system. And the reason is your laptop has one memory system, and all 8 have access to the exact same memory system. So the same physical memory. They can all overwrite each other's work inside that memory, which leads to a whole bunch of different problems that we worry about in computer science. And I'd love to have a distributed and parallel class at this university. We don't have that yet. Distributed is where each computer has access to its own local memory and none of the other processors do. So what happens with true, honest to gosh, parallel computing, the processors have to be geographically co-located. They have to be close to each other. And the reason is they're all talking to the same memory. They're all interacting with the same physical memory space. With distributed, now you can open up the geography. So in a parallel world, typically you have a computer that has one large physical box with the memory and the processors all contained within that box, large being a relative term. Our Vega down the street here, I suspect is parallel. I suspect that is all the processors in one unit with the memory, but I don't know. The difference is with the distributed, because each processor can has their own local memory. Now you can have a processor in Orlando, one in Chicago, one in Tokyo. So you're opening up the geographical space. Prior to what we have there now, is it Vega? Is that the name of that thing? We used to have a Beowulf cluster in there. A Beowulf cluster is when you take the motherboards out of a computer, out of a laptop or a desktop, and basically it's a processor and a memory card and a memory on one card, and then you take a bunch of those cards and you link them together via networking. And Beowulf computers are a cheap way to get really high performing computing. A few years ago, you can find online like the lists of the 20 fastest computers, right? The ones that do the most gigaflops per second. And like out of the top 10, 7 were Beowulf clusters, So you can have we had a 64 node Beowulf cluster. So in other words, we had basically 64 laptops or desktops acting as one unit. But they were distributed, even though they were in the same physical room, they were distributed because each processor only had access to its own local memory, and they communicated via the local networking. Okay, but like I said, once you say you're distributed, there's no limit on geography. We can do computer to computer message passing within this building just using the local network. Or we can do computer to computer message passing from this building to Paris, France using networking, right? The message pass, same kind of technique. And it turns out, depending on the languages that you're dealing with and the tools and all that, it's like trivially easy. Java was one of the first languages that was built implicitly to be parallel and distributed language. So they have really easy mechanisms by which you can say, hey, here's my IP address. I want to send a message to that IP address and have machines talk, because the idea was Java was the vision was that you would provide programs that were inherently distributed. Okay, so why are these simulations distributed? Like I said, if you have training simulations with a bunch of people, you're going to have a distributed simulation. Now the corollary to that now is with gaming. With gaming, parallel, distributed. What do you got?
For what aspect?
But the whole game. I've got a game and I can let 1,000 people play in the same virtual space.
Then that would be distributed.
It's distributed, and part of that reason why it's distributed is because each of those people have a game console or a computer at home, access to its own local memory, right? Then once they get into where the core of this thing is, presuming they have one processor there, then that has access to its local memory, right? So everybody has their own processors and local memory, so it's an inherently distributed system. It's also clearly not in the same room, right? You don't have to go to where the game is and go inside the building and play. You play from home. So that's distributed. Now, how could they do where they are at the gaming hub, wherever they have their servers set up? They may have a locally parallel system because they may have multiple processors playing that game for you with access to the same local memory. So that would be a weird hybrid system, right? Where they're locally parallel, but the overall gaming system is distributed. I'm only making these distinctions. Again, normally we say parallel or distributed, we don't care. Sometimes we care. And one of the reasons when you care is if you have access to the same memory, that's when you have to start worrying about things that we don't need to deal with in this class, but that's where you have to start worrying about things. Because if you have the access to the same memory, I put something in memory, Alex put something in the same memory block that I did. I thought I knew what value was there because damn it, I put it there. And then she went and changed it. Now my results are wrong. You see this when you buy tickets online. Why do you only have 10 minutes to select your seat on an airplane? There must be a reason for that, right?
I thought it was like to try to get you to purchase the ticket, honestly.
So don't double book a seat.
Yeah, while you're looking, they give you, right? They send to you a description of what seats are available. Yeah, exactly right. And so if you're waiting, that may have changed. The seat that on your screen says is available may not be available. So how do they prevent that? They lock the database, or at least portion of it. Now you've locked up the database and they can't sell any tickets until you buy yours. Oh, that's a problem. Okay, so they need to figure that out, right? Otherwise, if I'm Delta, I would open up all the other airlines' flights and never buy a ticket, and they could never book a ticket online because I locked all their databases. Right? So what do? It times out. A similar thing happens. I don't know if you noticed this with Canvas. Canvas is interesting. I can open up a bunch of different tabs on Canvas, and I can open up like the assignments tab, and then I can open up the assignments tab again in Canvas, and I can edit each one of those. And that's really not a good way to do things. You really need to figure out how you're going to merge the results when you do stuff like that. In Campus Solutions, if I open up a tab in Campus Solutions and I open up any other tab in Campus Solutions, the first one that I opened up is dead. I can't work with it anymore. I can only work with the second one. Why did they do that? To make me mad? No, they're protecting their database because they have both those tabs have access to the same physical memory. I don't know how it is when y'all are scheduled, when you all are getting your classes through Campus Solutions. Besides annoying, do they time out? Is it like, oh, I'm going to look at this class and see if I want it, and you have to do it within 5 minutes or something like that, or is it? But how long can you hold that page open?
It's just whoever hits the button first gets that.
Okay, so we can all try to get into CS362, and we're all sitting there for a day, not getting in. I mean, not even trying. We just open up the page saying we want it, right? And how does that look from Campus Solutions standpoint? Is it like, I want this class, how do I get it? I search for it.
Yeah, you search for it and then add a class to your schedule.
Yeah.
And then when it comes to actually get your class, you register. And that's the button that everybody takes 2 hours just to click and have.
Oh, okay. So you fill out your schedule,
Yes.
and then you click a final button that says, I'm done. Give me all these classes at the same time.
Yes.
Okay. So, yeah.
Registration actually doesn't open until at the same time. So you have your schedule.
Right.
But it opens at like 8 a.m.
Okay.
So everyone presses that button to register at the same time. Some people will get in.
What if you press the button at like 4 in the morning? Does it wait? It's like
it's locked.
It's locked. And then at 8 a.m. Okay, I see. So let's wait. Let's say at 8 a.m. all of us, we didn't do that ahead of time. At 8 a.m. we open up the tool, we schedule our classes, and then we're all going to wait till 8 p.m. to click register. You're saying though that if a course has seats open, if there's 5 seats open, all of us get in. Okay, so it's not what they're doing in that case is they're not locking the database so much as you don't have access to the database till you hit submit, and then they're going to handle all of the conflicts at that time in real time.
Yes. Oh, like I've left it open and then it goes and it's like.
Yeah, I've had that. Yeah, where it says you're inactive for X number of time. Yeah, you've been timed out for due to inactivity. Yeah. Yeah. And that's true. And that's just a generic across the board. No matter where I am in Campus Solutions, if I don't keep clicking buttons for a couple hours, it'll knock me out. Yeah. Okay. All right. I was wondering how that works. And so you can see what they're doing. They're protecting their database through the first come, first serve. And even though everybody technically, at 8 o'clock, we all click our buttons, there's going to be picoseconds of delay. And so they're going to come in first come, first serve. Yeah.
This may be getting into the weeds more, but going back to the plane ticket, how would that work with like third-party sites? Like if I'm booking a ticket directly from the vendor
Yeah.
and that locks it,
Yeah.
can't someone still purchase that ticket from a third-party site?
I'm not 100% sure. My recollection is that third-party sites will buy blocks of tickets from airlines. And and then I don't know if that restricts you to certain sections of the plane, like they buy specific seats, or if they buy a number of seats, and then they still have to filter it back to the airline about what's available. Yeah.
Basically, the airline. But an interesting thing to look at for that actually isn't plane tickets, but it's like concert tickets. Because you can buy them on like a bunch of different platforms like Ticketmaster and other ones, and there they do like block sell them.
Yeah.
And Ticketmaster is actually like a good example of what you were mentioning, with the like lockout, because they only allow like a couple people at a time to buy their seats, so you have to wait in line all morning long. It's like
Right.
it's
Yeah.
like you.
And then what gets me mad is I always forget, oh, I need to get my credit card and stuff. And by the time I get all that stuff, it's like, oh, you're too late. You gotta reload. And yeah. Those with the short timeout, I get very frustrated. And then I took a class years ago that was all about how these databases are managed. It's called asynchronous transaction management. And it's fascinating, all the levels of protection that they have to do. Basically, they do everything in a sandbox. And then once the sandbox is logically correct, then they'll copy it over to the real database. And there's all these management tools of, okay, we've gone this far in the process. We're gonna basically checkpoint like in a game. You made it this far, checkpoint, and then that way and anything past that you can roll back to the last safe version, that kind of stuff. It's a whole really cool set of techniques that they built up. And the same thing occurs here. Most of the distributed simulations are going to be like I said, the real-time human in the loop. Where you need to have a realistic response for a human in order for them to buy into the simulation, which generally means a training situation. Let's see, what kind of simulations do we have for training? Do you guys have to take? We have to take. Faculty have to take. What do I have to take? Oh, I have to take. I think I had to take like FERPA training. That was I just had to read through that. If you're a TA, you have to take FERPA training, right? If you're a grader. Okay. What was that? It's a video? Do they ask you questions at the end? In between? Is that a simulation? Yeah, it's a simulation. Because typically the way they ask you the questions in between is like, Bob and Mary did blah, 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 blah. What should Bob do, right? A, B, C. Yeah, it's a simulation because they're presenting you with this artificial scenario. It's a training simulation. We have to take, I'm sure you have, do you guys have to take cybersecurity training? Because you're an employee. So do you guys have to take it as students, cybersecurity training? We have to take, every year we have to take it as faculty. Yeah, and now what's creepy is the guy who did it died, but he's still in the video. What's his name? Yeah.
Changed it this year. It was like different this year.
Oh, maybe because he died. It was.
It's a lot of fire. apply, not just skip through.
Yeah, and then and we also get, do you guys get fake emails that are the phishing? We get the phishing emails, right? It's a fake email that tries to get you to, do you look at your email?
I get them from work.
Yeah.
Okay, yeah.
Oh, did
Oh, you're the one who does? Oh,
she's Alex is an employee. Are you an employee? Are you a, yeah, that's why. And then, yeah, and then if you click, in your email, it says you can report this as phishing. And if you do, they're like, congratulations, this was an IT had sent this out for practice. That's a simulation. Oh.
They know their
Audience
very well.
Oh, I've gotten two in the past year. One was with IEEE. And this was Dr. Liu. It said, this is Jinhua. I need $200 for this expense right away.
Oh, yours is like really? Like a.
Yeah.
Ours are not.
Yeah.
They're like, oh.
I mean, and that was an actual, that wasn't sent out by IT. That was an actual, someone trying to get, and again, all they do is they go through like the IEEE list roster of officers. And then they'll send emails out as if they were one officer. And I emailed Jinhua and I said, you didn't send this at all, did you? And he's like, no, I didn't. And then recently, someone used my name because I'm the Daytona section chair right now, and emailed another officer and said, as if it was me, and said, hey, we need the $1,000 or whatever for this event. And that guy emailed me and said, you didn't send this, did you? And I said, no, I didn't. So anyway.
I guess those are simulations. Those are Boeing has figured out how to make them really clever. Like I fell for it because they know exactly where you are in your employment. And IT, like at the beginning of my internship they knew that I was having PTO issues.
Ah.
So I got a scam email from their IT being like, we have resolved some issues with your PTO. Please click here for
Right.
something worked out.
And it looked really good.
It
Yeah.
looks really good. So they know that you're just employed.
And since they said Workday's screwed up, and Workday's always screwed up, it's very realistic. But that's yes, and that's a simulation, right? Because it was designed, it wasn't an actual phishing attempt. It was designed to simulate a phishing attempt. Yeah, the IEEE ones I was describing were real people trying to get money out of us. Yeah. Yeah. So, and I'm thinking, we don't have any money. Why are they wasting their time with us anyway? All right. So when you start into this distributed and parallel systems, as you would expect, you are introducing another layer of problems. And most of the problems have to do with maintaining consistency across all the different nodes or the different processors and memory units in the system. So what kind of issues can we come up with? Why are we doing this? Motivation, reduced execution time. So in the parallel world, if you have a computer and you're doing a highly intensive computational job, it takes time t. And then if you get two computers, if you do it perfectly, you're going to be at time 1/2 t, right? Because each of them is doing half the work. If you do it perfectly. Now, it turns out, even if you do it perfectly, it won't be quite half. It'll be like 0.6, right? Because there's a housekeeping cost with setting up the parallelization. So generally, the way that works, you have a problem, you have to break it up, send out pieces to the subprocessors. They initiate their processes, they do the work, then they have to collect the results back together. Well, while they're doing the work, that's the time you're gaining from the parallelization. So if you have two computers, the work is actually done twice as fast. But there's some cost set up with breaking up the problem, shipping it out, communicating back and forth. That slows things down. So even though I have two computers, I'm not going to do it in half the time. If I can do it in 60% of the time, that's good. If I have three computers, I'm not going to do it in 33% of the time. I'm going to do it in, say, 40% of the time. So how many computers can I get? Well, nowadays with cloud computing, you can do really cheaply, right? You can go to Google Cloud Services now, and for pennies, you can say, give me 50 processors. I need them for 10 minutes. And so we were working in Air Force, Masood and do you know Jason Clifford? Masood, Jason Clifford is a freaking genius that works down at Microplex. And I and a couple other people were doing some, Jake Neighbors, were doing some work with real-time learning with genetic algorithms. And genetic algorithms are really highly computationally expensive. And so Jason had set up this amazing system where these UAVs, simulated UAVs, were doing genetic algorithm. Yeah, I think I said you should probably talk to him. Yeah. So we were using the Google Cloud, and basically he would, when he was ready to run his stuff, he had everything ported up, and he would just say, "Okay, I need X processors, and I need them for 2.5 minutes." And you get the processors, you get the memory, right? So that's is it distributed or parallel? You know, from our standpoint, it's invisible as to which it truly was. I suspect they're all parallel because I think they all have access to the same memory space. But that's Google's problem, right? Not our problem. And it cost us like $5 a month. I mean, there's nothing. So you have access to those things for reduced execution time. So he was actually getting these things to run in, 3-4 seconds when they were massive amount of computations. You also get geographical distribution. So where do you get an advantage with that? For example, one of the ways you can train, like you guys getting called up for service, right? One of the ways you can get trained is they call you up and they put you in a truck and they send you out to the middle of the desert and you run around for a few days and practice in the real world, right? Now that's a simulation, right? It's a physical simulation. But another way to do this, and they do this with pilots, let's say, the complexity or the ability to train pilots via high quality, high fidelity simulations has been very good for a very long time. And so now you can have pilots in Washington, D.C. that are in a training simulation facility, and they're going to dogfight with pilots from San Diego, California, right? They're both physically in their cities, but they're in the same virtual airspace. So you can be geographically distributed. And this works well with the way the DoD is set up in our country because we have 1st Air Cavalry, I think, is down in Texas, right? That's the helicopter people. And the Air Force people are in different air bases all around the place. The tank training is set up in Tulsa, Oklahoma. But now you can have helicopters, tanks, aircraft all interacting in the same airspace and yet they're still geographically distributed. So you don't have to ship people around to training facilities. Now, is that as good as actually having them out in the real field? Probably not. It's probably pretty darn close, but probably not quite the same, right? System integration. The deal with system integration is we have that capability now to do what I just described, where the helicopters, the aircraft, and the tanks are all in the same virtual space. You can imagine how many decades it took to get to that point, though. And the reason is it was never envisioned that way from the beginning. In the beginning, the Air Force said, we're going to train our pilots using simulators. And everybody else was like, well, we wish we could do that, but we can't. And then the tank people finally said, oh, wait, we can do that for tanks, right? The helicopters are like, we can do that for helicopters. But they all did it independently. They got different vendors. They have different software systems, right? How are you going to make this all play together? So it took a long time and a lot of money to make it all work together. And even now, I'm sure it is not 100% integrated. But if you have multiple systems that already exist, it can be better for these complex systems to take the results of one and ship it via messaging to another rather than rebuild an integrated system from scratch. And then fault tolerance. So the idea behind fault tolerance is if one computer dies, and it happens, one computer goes offline, who cares? You just bring another one up. Or you shift that job to another computer. And again, that's a study in computer science, is how do we get teams of computers to work together? Oh, and by the way, if one goes down, how do we get the others to recognize it And did we save all the information that was on that computer so we can just redistribute that information and start it somewhere else? Those are, I think, really interesting questions. They're really, they're fun to work on. But you do get fault tolerance. Now, where might you get these kinds of things when different simulations? Where are we using simulations? Remember, we use them for, I've been talking in the context of training quite a bit. We also use them for prediction, so hurricane prediction. I would argue if you had spaghetti models and we have the US NOAA, National Atmospheric and Ocean, National Ocean Atmospheric Administration, NOAA, that their hurricane model, right? And then you have the European hurricane model. And there's not one model. Each grouping actually has several models. That's why you get different tracks out of each group, right? And so they're using, oh, we're going to use this model, we're going to use this model, we're going to use this model. Here's a bunch of tracks, and then we can try to average the results or do something to try to make a good guess as to where this thing's going to go. So we have the US model, which has multiple tracks, the European model that has multiple tracks. Assume that for now that those models can be done on a single computer at the US and a single computer in the European. Would you call that a distributed system? It's a good question, isn't it? 50-50 shot. What do you got? Let me make it easier. In our labs, like you can go upstairs in this building and there's a lab with what, 20, 30 computers. And there's generally students working on their own stuff in there. So that's each computer has its own memory local, right? Each student is, I know they can go to SharePoint, but each one is, okay. Is that a distributed system? Because they're working on different things. So they're independently, they just happen to be independently using their own computer. The thing that makes a distributed system is they're all working on literally the same computation. So in the case of the Europeans and the US, even though they're both trying to get hurricane models, are they doing the same computation? Are they message passing between the two? Or are they doing their own thing in isolation? They're doing their own thing in isolation. So that's an example where it's not distributed system. It just happens to be two people working on the same problem. There's a distinction there. So when we go back to the distributed system with fault tolerance, when you have the trick is the reason you know you have a distributed system is they're actually working on the same literal problem, message passing back and forth. Hey, I solved this part of the problem. Here you go. You know, you need this information to do your next part. The message passing, by the way, is where this thing gets slowed down. I mentioned the other day there was a group of people that wanted to do a simulation of 100,000 entities, and then they ended up backing it off to 40,000. And when they actually did it, it was to 8,000. And the reason was they had to do so much message passing between the different units so that everybody had the same state of awareness of where the simulation was. And message passing is really slow. You know, think about, I don't know, what's Wi-Fi around here anyway these days? How many gigs? It's up to gigs, right? Oh no, it's often megabytes still. Like internet is still megabytes, right? It's 15 megabytes per second or something like that. We have Spectrum at home and they claim that we're getting, I don't know, 200 megabytes a second or something like that. But in reality, it's probably like 20 megabytes per second. How about your computer? How fast is your computer? How many operations per second does it do? Usually it's like 3 or 4 gigs easily these days. I mean, I think mine is like 2 gigs and it's old. So compare that. 2 gigs compared to 2 megs, let's say, that's a factor of 1,000, right? Even if it's 20 megs, that's a factor of 100. So in other words, what I'm getting at, the message passing is 100 times slower than the computation. So where are you going to find your bottleneck is? It's in the message passing. And that's why those people wanted to do 100,000, could only do 8,000. It was because of the message passing. Each computer they had at the time was loaded up with as many entities as they could to keep the real-time interaction real and not delayed. And so by the time you add enough computers to try to get to 100,000, you've got too much message passing because everybody has to pass to everybody else. Now, if I've got 10 computers, I've got 100 connections. There have been mechanisms introduced, we'll talk about it in a little bit, to try to manage that. Just managing the information space. Right? So there are tools that have been developed for that, and there are issues with those tools, right? So here's our motivation, but here's our issues: latency and what we call fair fight. So a fair fight is a result of the latency. So latency means that there is a delay between the time when you do something or request an action to be performed and the time that that action shows up in your portion of the simulation. Remember, in a distributed simulation, you have on your local machine a portion of the computation. You want to have a full view of everything, but you have a portion of the computation. So if you do something on your machine can do that computation very quickly, but then it has to transmit that new state to other machines, and you get latency. Or if they do something, it can take time. And again, what's the big thing with gaming, online gaming? Latency is an issue. Why do they limit you to X number of people on a server? Latency. Now, remember, latency is going to be consisting of several parts. I want something to happen on my end. That means I have a computation. That takes time. I transmit a message. That takes a lot of time. A computation occurs at the gaming center's end on their server. That takes time. The message comes back. That takes time. My machine has to recognize that. That takes time. All of that can add up. Now, in the real world, as soon as something happens, you see it, right? Speed of light. So in the real world, we don't have to deal with latency. We can make up examples, right? Like if you see somebody hit a hammer on a metal rod a quarter of a mile away, you see it immediately, you hear it, what, a second or two later, right? So in the virtual world, though, you have to make things appear as if they're happening instantaneously to the human. So we have a low threshold of how much delay we can handle. If there's very much delay, you start doing bad things like, if your machine is a little bit locked up and you press a button and nothing happens, you might press it a few more times, which is probably not the right thing to do, right? So we behave poorly because of latency. That leads to something called fair fight, which again, this is specifically about DoD training. Basically, it means if I'm in a building and an opponent opens the door and shoots me, but I wasn't even told that the door was open, that's not fair, right? That is not a fair fight. We both have to be apprised of what's happening at the same time. That's fair fight. And it's about latency. And again, the gaming community has been dealing with this for a long time. And there was it seemed to me, I'm not a gamer, but it seemed to me from the indirect chatter that I hear that was creeping up. Like first of all, when everybody was doing dial-up, there was no online gaming community to speak of. It existed, but it was, right, it was a lot smaller. And then as the speeds keep getting faster, the messaging speeds particularly keep getting faster, the quality of the games got better, the graphics got better. Why did the graphics got better? Because they had faster chips so they could process the more realistic environments in real time. But there was this like a kind of a peak of, oh, but there's latency. And then that seemed to go away. They seem to have largely resolved latency issues through a couple of mechanisms. One is the chips did get faster. Two, they got very clever about how they process environments and actions. And three, multiple servers. I think that's the big one, right? They limit you. And that's why. So you get fair fight. And again, virtually all the games online are fighting games, right? They're almost every game online is pro-violence. So that's what these are. These terms are about. So consider some simulations like the astronomy people try to model things like how do galaxies form or how do stars form. What's the working model? The working model is there's a bunch of gas and it starts to collect, right? Gravity. And then once you get small units, they have more gravity, so they start aggregating more. And over time, they aggregate and aggregate and aggregate until you have a star, right? And this happens at a larger level until you have a galaxy. How do they interact with each other? People do try to model that. And they try to model that, think about this, with hundreds of thousands or millions of individual entities, each of which is having a gravitational effect on every other entity. It would be like real time. If you tried to do this on a single processor, right, it would be like a real time. We can figure out how the galaxy forms, but it takes us 3 billion years for the computation to end. So what do? That's when they use these computers like Vega. So that's an instance where even though you didn't have a need and from a training standpoint to keep the latency low, the actual computation has so many computations that it's infeasible to do on one computer, so you do it on multiple computers. Similarly, people who do fluid dynamics. Fluid dynamics is a huge computational cost. So, there's a COIS, they've got a wave machine. They're very proud of their wave machine, right? And they also try to do digitally. They try to predict what will happen in the wave machine. That's a lot of computation. I think those people are using Vega too, probably. The EP people, and a couple of years ago, those were the people that were using our computer a lot. Because they had the kinds of computations they were doing were so what we call high performance computing. So many computations are needed. Digital air tunnels, the digital wind tunnels are a big thing now. We just spent $10 million on a physical wind tunnel. And I'm like, oh, I could have done it for 100,000. I could have got you a digital one for 1% of that cost. That's a big deal now. Why are digital wind tunnels a big deal? Number one, they're cheap. They're cheap. You can reconfigure really easily. If you want to use a real wind tunnel, and they are neat. First of all, you have to build the real wind tunnel. 10 million bucks. Then you have to build a physical model. What if you want to modify the model? You have to build another physical model. As opposed to in digital world, what if you want to modify the model? It's a different ACAD drawing, right? It's just you go back to ACAD, change the drawing, port the model over. So there are times when and what if you want to change the shape of the wind tunnel, of the digital wind tunnel? The real wind tunnel, you can't. They do put in, usually they have each real world wind tunnel has what's called a test section. And often the test sections you can take out and they'll have a bunch of different test sections. So you can put different ones in based on what the size of your model and how much airspeed you need, that kind of thing. So in our wind tunnel, that expensive one, they have, I believe, multiple test sections. And so, by making the test section smaller in area, you can get more faster airflow through that section. So that's why they do that. But again, how can you do that digitally? Right? If you design the product right, You're just setting up some parameters. So the cost is way down, but think of the computation. Oh my gosh. They do it a lot of times through thousands and thousands and thousands of little tiny boundary volumes. Is anyone here taking fluid dynamics? You took fluid dynamics? Remember the control volume? So you do this, that's how they can compute things. Thousands and thousands of control volumes. And then what you have to do is you have to make sure that you satisfy conservation of momentum and conservation of energy as you go from boundary to boundary layer to boundary layer of these different things. That's a lot of computation. So how do you do it? Again, that would be a case where you'd want to use a parallel or a distributed system, just because it's so computationally intense. The other way if you need to lower the computational cost, is you make the model more coarse, right? You make the control volumes bigger, so there's fewer of them, and if there's fewer of them, you have less computation. But if you really want to get good results, you want to have a fine-grained system for these physical models. So these are cases where you have really high a degree of computation. Again, there's a whole section, you can look up high performance computing, and that's a whole sub-community within the computer science world of high performance computing. Specialized algorithms, specialized weighted to use parallel and distributed systems, things like that. So that's why these things exist. Now, again, in our class, are we going to use them? No, we're even though technically your laptop is probably technically a parallel system at this point, we always treat it as a single computational unit. It behaves like a single computational unit. I don't know. Do you guys know of any situation or of any kind of tool or modification to the operating systems that you can get that you can treat your machine as a truly parallel system? I think all the parallelization is done in the operating system itself. And from your viewpoint, it's always one processor, I think. Do you know of any? It's got to be out there.
I think with like overclocking, you can pick specific cores to do
So that's a load balancing thing, yeah. So okay.
but that's about it.
Yeah. Okay. Well, there you go. So anyway, within the context of this class, you don't have an opportunity to explore this very well. But it is if you're going to go out in the real world and say, hey, I know something about modeling and simulation, you should at least know that in the real world, you're probably going to encounter this and know some of the terminology. Let's go through this, this. So I said that there are systems that were developed to work with these distributed and parallel systems. And the most famous one is called, this information might be a little dated, but it's called high-level architecture. Now, high-level architecture used to be a big up-and-coming thing in the modeling and simulation world. And the reason it was is because the DoD was buying into it big time. And what high-level architecture was doing, it was trying to set up a framework by which if you created a simulation, you would create it in such a way that it matched the template that high-level architecture wanted. And we talked about accreditation the other day. You could get accredited by the high-level architecture people and say, yes, this really is a verified high-level architecture design. Therefore, it plays nicely with others, and it helps us do integration. And this was developed through the DMSO, the Defense Modeling and Simulation Office, which was part of the DoD. And the Air Force had one. There was an Air Force DMSO. There was an overall DoD DMSO. There was an Army DMSO. So there was all these defense modeling and simulation offices. And about 20 years ago, for some reason, all their budgets just got wiped out. So they may or may not exist. I don't know if they ever got reconstituted. Army has, every branch of service has this, but I'm only familiar with the Army. At the time, they were called STRICOM, which was Simulation Training and Instrumentation Command. And they got redesignated as something else, but Stricom was in charge of the DMSO office for a while until it went away. So again, you can look it up and see if it got reconstituted. I'm not sure. But they worked with industry and with academia to develop this really high level architecture, a very comprehensive description of what it would look like to create simulations that had certain characteristics. And one of the things, the basic thing, was an object model. So what do you know? Object-oriented software design made its way into this thinking, and you create an object model that has certain specific attributes and certain ways that you present or construct your model. And if you did, any HLA compliant simulation should be able to suck in that model and work with it. Again, it never worked that cleanly, but that was the goal. Then when you create a group of them, they called that a federation. So you would have a federation that was a collection of these simulations. And the federates were collections of object models. And then I said that information management was a difficult thing. They created something called a runtime infrastructure, which was a information management system. It's a great system. It's still out there. 15 years ago, I was working with a project with MIT Lincoln Labs, and we were testing FAA air traffic controller behaviors, real-time simulation. We're throwing different simulations at them and watching how they responded. And the MIT Lincoln Lab people had created this simulation from scratch. And I said to the head of the project one day, boy, you really should turn this, make sure that you turn this into an HLA compliant simulation. He's like, oh, we already have a version for that. They already knew where they were going, right? They wanted to get DoD funding more. So they were getting FAA funded. They knew they wanted to get DoD funding. So they were already compliant with that. They had another version that was compliant. The runtime infrastructure was a concept, and different vendors attempted to create software that behaved like a runtime infrastructure. And I'll describe how that works in just a second. And that was a real problem again 20 years ago. I'm not sure, quite frankly, the state of HLA right now. If it's been abandoned by DoD, if it's been abandoned by industry, if it's still living on, I'm not 100% sure. We can look into that. The runtime infrastructure worked on a publish-subscribe system. Publish-subscribe systems are pretty straightforward. Here's the deal. Let's say we wanted to model airspace, and we're modeling all the airspace in North America, right? The NAS, the North American airspace. And here I am, I'm in my simulated airplane, and I'm a little Embry-Riddle plane on approach to simulated Daytona Beach Airport. So I'm in my simulated Embry-Riddle Cessna 172, and I'm simulating my way into the Daytona Beach Airport. Do I care that there's a 737 landing at Los Angeles at that moment? Probably not. I don't even care if there's one landing in Jacksonville, right? So here's the thing. I can have all these different entities, and at any point in time, there's something like 5,000 aircraft active in the North American airspace. I don't need to know what all 5,000 of them are doing. I need to know what's happening around me. So if we all did message passing, all 5,000 to 5,000, that's a lot of wasted message. And remember, once we get into message passing, if we're using internet links, or network linking, then that really slows everything down. Plus, my computer has to process 5,000 messages every second to find out which 3 are valuable, right? So that's dumb. So instead, what we do is we publish and subscribe. So every time my model does something, it publishes a change in state. I'm at this position, this location, this heading. And then half a second later, I'm at this position, this heading. And I can keep doing that whatever my publication rate is. If I'm sitting still, I don't have to publish at all, right? Because I didn't change anything. I might publish like every minute. I'll publish what we call a heartbeat, because you need to be able to distinguish between a model that is inactive but present in the simulation and a model whose processor died. Right? You need to be able to figure that out. So we publish what's called a heartbeat. But I'm going to publish and publish and publish. And then other entities are going to subscribe. And what are they going to subscribe? They're going to say, I want to know about aircraft that are within this latitude, this longitude, this latitude, this longitude, this altitude. I'm going to set up basically a bunch of conditions for my subscription. And then what the RTI does, it gets all the messages and it says, okay, you subscribe to these messages, I'm going to send them to you. You subscribe to these messages, I'm going to send them to you. You subscribed, I'm going to send them to you. So what it's doing, it's an information management system, and it's supposed to cut down on the amount of messaging traffic we have, which, as you recall, was the limiting factor in these distributed simulations. Now, the problem was you had a distributed simulation, and the first generation of RTIs was one RTI. So now I've got a distributed simulation, but all the information management was not distributed. It was a single processor, and it was a bottleneck. They were horrible. So the next generation were they just distributed RTIs also. So RTIs were collecting local information, passing along what it needed to other RTIs, and then passing it along to the entities. But that's the kind of, again, it's an interesting problem, in my opinion. That's the kind of problem that people had to solve to try to develop these distributed simulations. You can imagine an easy way to do a distributed simulation or any kind of distributed computation. If you have a map, a large map of terrain, you can just carve up the map, and maybe each of us, there's 5 of us, each of us gets 1/5 of the map. Great. Now we can compute things 5 times faster, roughly. However, anytime something happens at the edge of my map, you might need to know, right? If we have a border area on our map, then you need to know about it. And if any of my agents went from my map to your map, I need to tell you about it, and I need to transfer control of that agent from me to you. So these are the kinds of problems that show up. How do you handle that kind of stuff? And so there can be some real, I think, interesting work there. If you're doing, you want to get a master's degree, this is a field where it's still challenging enough. The problems are still open, so you can still get some research done and then try to get a thesis out of it. Think about you're presuming vehicle-to-vehicle communication. How does that happen? Probably a publish subscribe. There's probably going to be a message broker at some point. Either that or, everybody's just broadcasting locally. Maybe. Then we all have to agree on frequencies. And the car companies have to buy those frequencies from the FCC.
Or at least
Or lease them, right? Right? Or I can now spoof. The security issues. I can inject signal as if I was a vehicle on the road, right? Even though I'm not. Or jam, yeah, all kinds of things. So it may be that they use a lot of vehicles have like an OnStar service, right? So they may use that as a message broker instead of going directly. I just broadcast. I go to a message service. Maybe not. Maybe we do like aircraft do. Aircraft now do ADSB, which is not using any kind of a message broker, right? It's just direct. I'm broadcasting, and if you can pick up my signal, and then you can interpret what I'm saying. Yeah. Okay, that's plenty for today. We'll pick up more with this tomorrow. Questions or issues or concerns? This is, like I said, I really like this stuff.